No. How do I see that? How do I know that it's not time invariant? If I shift this sample this by 1, what do I get? I get 0, 2, minus 1. Okay? If I take this one, I shift by 1. Right? This sample go to 1. It will be dropped. Right? This sample go to 2. It will be kept, and so on. You can show that if I shift it by 1, I'm retaining the odd index sample. I'm keeping 0. Right? With the minus 1 sample, this one is 1. So this is not time invariant. It is invertible. Let's show a hand of yes. Show a hand of no.
Yeah.
No. Yes.
No.
Is it invertible?
No.
No. For this example, okay, doesn't look like it, right? Because I have no idea of what is the one in the middle. Okay. However, there are some cases that it is invertible. So this is a maybe. I will show later on in the frequency domain the condition on the signal X such that it is invertible. So this is condition on X of e to the j omega. Okay? Any question? I want to discuss how y of e to the j omega, of e to the j omega. And here is the case where it is not simple to derive. In upsampling, it's very easy to derive, right? Upsampling, we insert 0 sample. There's no information. We just scale the time index from 1 to 2, 1 to L. And therefore, x e to the j L omega. In this case, here it's very different, right? So how do I find the relationship in the frequency domain between x and y? Any idea how to do that? Okay, let's take an example. Okay? This is n 0, 1, 2, 3, 4, and so on. That's the index n. X of n, x of 0, x of 1, 2, 3, 4, 5. Here, basically the general way of, denote the sample. You can take any value here. What do I want for y of n? What's y of 0? X of 0. What is y of 1? 2. X of 4. 6. So y and u together in frequency domain. Right? But what is it? What is u of e to the j omega equal to? Y of e to the j 2 omega. I'm going to relate u to x. And then we're done. Is that clear? How do I get x to u? What do I need to come up with another sequence here? Such that when I combine together, I drop all the index sample. Why does this sequence have to be? X of 0, right? Equal to me minus x1. Add together gets 0. Okay? This is x2 minus x3, x4 minus x5. This additional sequence allow me to cancel out the odd index sample. And then relate to x, right? What is it? minus 1 to the n x of n. We've seen this before in a filter set. But you can apply this operation on any digital signal. Right? Okay? Now, what is u equal to? X of n added to minus 1 to the n x of n divided by 1 half. Right? Is that clear? When we do this, what happened then? On index n. What happened to n equal to minus 1? X of 1 minus x of 1 is 0. And so on. Right? So this actually cancels out all the odd index sample. And then when even index can be divided by 2. So what is u of e to the j omega equal to? X of e to the j omega, and this is shifted by 5. Right? So here we relate u to what? Right? So we have u related to x, and u also equal to y. So now y is related to x. Okay? So how does y of e to the j omega equal to? Now we change the omega to omega over 2. So the final form will be follows. Y e to the j omega equal to 1 half x of what? 1 half. Over here is x of. So we have, let's see, here, right? So e to the j omega over 2 minus pi. Okay? Right there. Okay, rewrite this in a more useful way. E to the j omega minus 2 pi over 2. It's the same, right? Omega over 2 minus pi. Any question on this form? That's our final form. So what happens when we downsampling? Is we have the original signal compress or stretch? Stretch. That is the opposite. Downsampling in the time domain we compress. Frequency domain we stretch. Right? So here is the stretching operation in frequency domain. What happened here? Yeah, some additional factor coming in. Okay, so let's do this. Let's visualize this through an example. Okay, so here is, suppose this is again x of e to the j omega. Let's say 0. So let's pi over here, and pi over there. This is 3 pi. Over 4. Okay, here's an example. So let's draw y.